So for the folks just joining, for the folks who don't know what's going on, this is a stream where we'll be talking a little bit about statistics as priestcraft. It's descriptive statistics part 2. Part 1 was last week. Don't worry about going and watching that now. You can always watch it later. It's available in the Discord or on my YouTube channel. What were you about to say about Bella?
Oh, she like, you walk into a room and you look over and she's like laying on the couch or something, and all you see is just a little tail going wiggle, wiggle, wiggle. Wiggle, wiggle, wiggle.
That's Dogs and Radicals just introducing himself, talking about being a tutor of math and statistics. Is that right?
Math, science. So I can do introductory, like physics, chemistry stuff, mathematics, usually like high school, like introductory calculus, a bit of differential equations, a little bit of vector calculus. Like, I can do more. It's just I don't lecture that stuff. So there's things that I can do that I don't really teach, and there's things that I do a lot, so I teach. And statistics is in there as well.
Always fucking with. So because I don't have my webcam, my actual webcam right now. This thing is on a pile of books, and sometimes I need one of the books, and so it's always getting moved around. But my the virtual classroom fundraiser that has not gained a dime in my last 20 hours of streaming since the last time that I Am Object made a donation. That once that is finished, I'll be able to get a webcam that's a real webcam, not one that does all this refocusing, one that has one that I will own. I don't own this one. I'm just using this one for now. This one's just someone else with, like, on loan, so that I'm able to do this virtual classroom thing where I have, because otherwise I used to always just stream with my other camera. My other camera, though, is the whiteboard camera. This webcam I'm using someone else's so that I'm able to use both. So I can swap between, see right there, everybody? That's the whiteboard. And we'll be using that. And then this is like the camera that I'm currently using. But as soon as we get the new camera, and also green screen, because that's what the fundraiser is for. It's for, on the one hand, a green screen, on the other, my own webcam. As soon as we have that, I won't have this issue of books. It'll have its own little tripod. And the books can be somewhere else. But anyway, yeah, it's like I'm constantly having to like reorient things to just get it right, however I have it. But anyway, speaking of the whiteboard, though, so I guess for quarantine specifically, it's like been the time. The time is now to be experimenting with this virtual classroom setup, and I'm doing it by doing an Intro to Philosophy lecture series. I'm doing an introduction to psychology in the continental philosophy tradition, which is an introduction to Lacan with the dangerous maybe. And then we're also doing this statistics, politics, and we're calling it, our conversation like 45 minutes ago, now I'm calling it, from now on, this course is about neo-feudal priestcraft. What does that mean to you? What does priestcraft mean to you? Yeah.
Well, it's what you think of, it depends on what you think of priestcraft as being. The book that I shared there brings the analogy of if it's a body of knowledge that is only really used by a group of specialists up in their ivory tower, kind of separate from the everyday working, then it's a sort of priestcraft, and it will like eventually start like accumulating a bunch of dogmas and ways of doing things, and it becomes incredibly like rigid and inflexible in that way. And like a lot of academia has undergone a little bit of that process of, as things become only the realm of certain sorts of people being able to do it, and the bodies of knowledge become like inaccessible, this like just complete disconnect between things. And the analogy that it gives is back to what Plato, Socrates. Who is the one that wrote, and who's the one that was the teacher?
Socrates never wrote. Plato wrote.
Okay.
Yeah.
So it was. I think Socrates' theory of like how the world works, and like the head is a sphere, and it's like a perfect shape, and this is being all about like, oh, academics up on their ivory tower. This is very flattering to them. How their models of, oh, like elements are either like different types of triangles and stuff like that. It's like, oh, good lord! But that's all in this book, and this book is a fun little thing if you would be interested in a historical perspective on all the mathematics that you learn in school, instead of the unit by unit. Let's do this to do this task, and let's do this to do this task, and let's do this to do this task. And oh yeah, no, you don't need to understand why these things are all similar to each other. You just need to be able to pass the test so I can get my funding, so this system can keep on going. But instead, this takes kind of a historical view of all this stuff, where it came from, what are the weird problems that were stumping the people thousands of years ago, and like why Mr. Pythagoras and the triangles of the time, like he was in the Library of Alexandria staring at the pyramids, he didn't formulate the Pythagorean theorem as we know it. Like, well, he formulated the theorem aspect of it, but like that relationship is ancient. And you can draw little pictures of it. There's nice little drawings from China, like a good while before that, and before that it was part of the oral tradition. And like, this is an international thing. It's a worldwide thing. It's something that we do all over the place.
Now we talk about Pythagoras. We've brought him up before, so let's spend a second doing that still. Like, okay, my impression of Pythagoras before before college was Pythagoras. It's the theorem. Like Pythagoras was an early mathematician. Okay, mm-hmm. I couldn't tell the difference between Pythagoras and any of these other people that we talk about, Socrates or whoever. But Pythagoras was really interesting. He had a cult. He had a cult of numbers, and they worshipped numbers. Some of Plato's ideas about the forms probably come from Pythagoras's cult that worshipped numbers. They killed a guy. They killed at least one person because the person was talking about imaginary numbers, which is real. Yeah. Imaginary numbers are real, but someone got killed.
Imaginary numbers would have meant something very different to them as what it means to us. The like forms and shapes, and like I think of them as like size relationships between things, but like there's still aspects of that idea of forms and stuff present in a lot of like mathematics. Like I use like a straight line is a shape, a quadratic curve is a shape, an exponential is a shape, a sinusoidal is a shape. There's lots of different shapes, lots of different patterns that you learn as you keep going through stuff. Yeah, lateral numbers, 2D numbers, exactly. That's modern imaginary numbers. But imaginary numbers to them would mostly have been irrational numbers, which are your pi, your square root of 2, and stuff like that. Because those are numbers that cannot be represented in a traditional way, because they have a infinity aspect to them that's impossible to like break it apart. It's really weird to really get your handle on it. So you kind of refer to these numbers indirectly. Like the square root of 2 is the number the square root of 2. It is referred to by a verb that tells you how to get it and what you do. The square root is an action. It's telling you how to get it. And it has consequences. It is the number such that when you square it, you get 2. That's what the square root of 2 means. So the square root of -1 for imaginary numbers is the same thing. It's the number such that when you square it. But like, it has applications. It has other numbers in really fascinating ways. And multiple times I joked about like starting a new a neo-Pythagorean cult.
Welcome everybody to our new cult. Here, I'm gonna actually I'm memeing this right now, actually. So.
Oh yeah, no. It's like
I don't have eyes on chat.
But time, like the existence of transcendental numbers argument math is discovered, not invented. Yeah. In some ways, yes. In some ways, like that's a really interesting distinction whether it's discovered or invented, because like the fact that you can then use it for things like suggests it's always there in a sense, but like humans not having a way to grasp it until they come up with new things, like different concepts not making sense. Like to the Greeks, they didn't have time. They did independency within their mathematics because everything was geometry based. So
okay, there we go. I made it. Praise be to. So that's Pythagoras and his little cult, and they're praising numbers. So.
Yeah, well, it's not even numbers. It's really geometry at that point, because numbers aren't even really a separate thing until much later, until algebra. Because the numbers of that period were mostly they were mostly the tallying system for what they did with their abacuses. Like,
okay,
it was like the abacus was higher in the ladder of what was important, and the symbols that were used to represent what you did on the abacus were a ladder thing. They referred to the abacus itself. The idea of doing the mathematics purely on the numbers, not really a thing with me, and algebra and all that stuff, hundreds of years later.
Okay, I fixed it then. I made a new one that says
praise be to triangles. It's praise be to triangles mostly.
Okay, fuck, now I gotta do it again. All right, I should have asked you. All right, hold on, I'm gonna export a new one that says praise be.
Praise be. Oh, geometry works. Geometry works.
Does it? Are you sure?
And praise be geometry down with beans.
Down with what?
Legumes, beans.
Is that what? What do you mean?
Oh, that's real. That's real.
What were they saying? Why is that real?
Because he had a thing, but he hated beans. This is not even a joke.
Just all beans? Coffee beans too?
It was like, I'm not sure specifically what beans it was. I think it was just legumes and let's see, Pythagoras and legume and beans is like the first thing that pops up. Where is it? It's on the. Some medieval authors refer to a Pythagorean diet entailing the abstention from eating meat, beans, or fish. Pythagoreans believed that a vegetarian diet fostered a healthy body, enhanced the search for eret in a basic sense means excellence. Okay, and enhance the search for their conceptualization of excellence. The purpose of vegetarianism in Pythagoreanism was not self-denial. Instead, it was regarded as conducive to the best in a human being. Pythagoreans advanced a grounded theory of the treatment of animals. They believed that any being that experienced pain or suffering should not have pain inflicted on it unnecessarily, because it was not necessary to inflict pain on animals for humans to enjoy a healthy diet. They believed that animals should not be killed for the purpose of eating them. Pythagoreans advanced the argument that unless an animal posed a threat to humans, it was not justified to kill an animal, and that doing so would diminish the moral status of a human. By failing to show justice to the animal, humans diminish themselves.
Well, they were the original vegans.
Yeah, vegetarian.
Okay. Well, and like, obviously they weren't original because Hindus were way before that.
Oh, yeah, yeah.
You know, but in, you know, yeah, as far as the Athenians go, yeah. Mm-hmm. So there we go. I fixed it, y'all. It says praise be geometry down with beans.
Yeah, apparent like the biographical tradition on Pythagoras holds that his mother, wife, and daughters were part of his inner circle. Women were given equal opportunity to study as Pythagoreans and learn practical domestic skills in addition to philosophy. There's some interesting stuff in like Pythagoras. Like, yes, he was a cult leader, but like also in a lot of ways was ahead of his time in a lot of different different ways. But that's the nature of that sort of thing as well. radical
What?
traditions in all their forms, because it was a sort of radical tradition.
What a champ. Yeah. Well, and I guess the last thing I'll say on that is that the last thing we'll say about at least that I'll say about the history of this stuff, like when I first started finding out about Pythagoras and all of this, I also found out that Socrates, kind of the original political philosopher, because, up until political philosophy, nation states always just defined power and justice in accordance to might makes right. And so, if you want to go back before philosophy, if you want to do things before philosophy started trying to do things, you just go back to, you do it because we say it, and we'll kill you if you don't. Philosophy, from its very inception, has been, okay, but how are you going to try to justify that? And what would be real justice? Let's talk about real justice. And so, Socrates is one of those people. But when Plato, one of his disciples, after Socrates was put to death for being a philosopher, Plato, his academy, over the top of it, it said, let no one who has not studied geometry enter. Right? Like, basically, geometry was the single prerequisite to studying everything else, because they thought, like Einstein, that if there is a rational coherence to the universe, then geometry was it. Now, things change over time. People think, there's a more fundamental physics or a more fundamental mathematics, but that was definitely theirs at the time. So. Yeah. So anyway, we're talking about this being neo-feudal priestcraft. It was also obviously feudal priestcraft. Zanzi mentioned that it was developed by Scottish priests to make sure that, I don't know, you'd have to reshare that story and maybe a little expand on it. It didn't make a whole lot of sense to me. That it was something about getting widows like pensions or something. But anyway, mathematics and statistics have always been used by the ruling classes to control for certain outcomes, and at the same time manipulate or even sometimes gaslight the peasantry, right? So here we are. I'm a plebe and you're a tutor, and we're going to get into some statistics now. And the homework assignment, let's bring up the homework assignment. Here we go. Was, I'm gonna zoom in on it so people can see what is said. Let's see. All right. If the income of every person in the United States was used as a data set, and someone wanted to describe where the center of that data set is, what is the effect of using mean as the center as opposed to using median as the measure you use? How does the number differ? What are the different numbers? And now, so I'll just say this much before I turn it over. To me, mean just means average. You take if I were to take everything and then divide it by the number of different number. Okay, if I take 10 people, and I divide whatever the different. Fuck, I can't even define it. You divide it against itself, right? So you take the total aggregate and divide it against the number. Yeah.
You divide against itself. What property of the thing is being divided?
That's what I guess I can't answer. That's why I'm stumbling here. How would you say that?
It's the weight. It's a number on a scale of some sort, which will have some sort of some units associated with it, and the like. So you can average like weights, heights, years, anything that can be measured in some sort. It's a weighted average. Each individual object can like drag up the weight if it is higher than other numbers.
So that's kind of like when you talk about someone skewing the curve for a class.
Oh yeah.
Let's just say everybody in the class is doing what would normally speaking be C work, and then you have a professor who's going to apply a curve, meaning that if most people are doing C work, then the person who's doing B work is actually going to be doing A work. But if you have someone in the class who is still doing, by the old standard, real A work, now all of a sudden you got people who are going to be like, oh, you're fucking up the whole curve. You're skewing it.
Yeah.
So, and that's because they're using a mean. Is that right?
Yep. Yeah, kind of. The difference between, so the mean cares about an actual scale being involved of these numbers, and a mean is a bit troublesome when the differences between your numbers is no longer the same. So if a doctor tells you to rate your pain on a scale of 1 to 10, like, because everybody's going to rank this a little bit differently, and the difference between like a 7 and an 8 and an 8 and a 9 is not the same thing.
Hold on one second. Sorry, I was responding to Good Workout Buddy. By the way, welcome, Good Workout Buddy. It's good to have you. Oh. It's always good to have a good workout buddy, especially this one in chat. But what you came in on us discussing this right above my head, and so if you already have a basic sense of the difference between mean and median, then you're probably ahead of me, because I mean I'm kind of getting what mean is, and right now Dan, aka Dogs and Radicals, is explaining how weight is how weight plays in, and that's where I'm at.
Yeah, and a mean is something you primarily do on like scalar family numbers. So things where the differences between 1 and 2 and 2 and 3 and 3 and 4 are all the same. And that kind of needs to be the case. It needs to be kind of measured in units, and those differences need to be kind of fixed and understood. And in situations where you have numbers
fixed
where that...
and understood, okay.
Yeah, and when you have examples where, like I said, rate your pain on a scale of 1 to 10. Like a 9 to one person might not be the same to a 9 to another person, and the difference between 8 and 9 to somebody might not be the same as the difference between 7 and 8. And in that sense, what is really going on, you have ordered numbers, an order of things. And median is fundamentally about the order of numbers, or in math parlance, the rank. So 1 in median is the lowest rank, and however many numbers you have, that will be the highest rank. You just order them from 1 to the highest number.
Okay. And
when you analyze something via a mean, you can have outliers that drag your numbers way up or down.
So if you have a billionaire, if you have a society with a handful of billionaires, you can have it be where, okay, so if 4 people own more wealth than the bottom half of the country, but people are telling you what well, I guess in that case, the mean is going to be very skewed. And I think that, and this is going to get us to why median is better to go off of?
Well, median is different.
Okay.
Median doesn't care about the size differences between the numbers. It just cares about the order of the numbers or the ranking of the numbers. And that's me throwing terminology out there. Is the rank is usually how they talk about it. And this is mostly, well, these are just different forms of analysis that will appear depending on like the different quality of data you have. Are your numbers on a scale, or are your numbers ranked? Are they mostly ordered?
Okay, can we talk a little bit more about the difference between scale and rank? So really quick. So scale versus rank. When rank makes sense in the sense of that, like, you know, things are ranked from highest to lowest, or lowest to highest. And, you know, when I think of rank, I think of the military and people being, you know, promoted in their rank. When I think of scale, I think of scales, right? But in math, when people talk about scales, I usually get lost really quick. So maybe you could use maybe a metaphor or an analogy that'll make more sense to me.
Fundamentally, when I'm saying scales, I'm talking about something that has units associated with it.
When you say something that has scale, it just has units?
It has units associated with it. So feet, meters, miles, seconds.
Those are all units.
Pounds, kilograms. Exactly. These are all units. And when I say a number of things, I can talk in terms of a number of units. I can talk in terms of number of pounds. I can talk in terms of a number of feet. I can talk in terms of a number of inches, and I can make equivalencies between those two things. Oh, I have yes, yes, scalar. This is similar in the distinction between scalars and vectors, in that you have lower quality numbers and higher quality numbers, but this is not scales in the same sense. This is scales in terms of measurement, in terms of like this is scale like the this just to
this distinction hurts my brain. So
it's like beginning. It's fundamentally about, is the difference between two numbers constant or variable? Like, is 1 versus 2 versus 3, is the difference between all of those the exact same different amount?
Yes.
Or is 1 versus 2 versus 3, is 3 just saying 3 is above 2 and 2 is above 1? Is that all you're saying with that line of things? Or are you saying that the difference between them are fixed increments that can be picked out and added together to create concrete distinctions along a line?
Okay, so what's a good example of counting something and how... What? I guess
it's anything that's measured in a unit, really. Scale. Be it a temperature scale, a measurement scale, a weight scale, a volume scale, between each of the numbers is the same amount, regardless of how big you are. You're dealing with a scale.
Okay.
And dollars could be a scale, because dollars is a unit.
And now, how does that vary from rank?
Rank, I just rank. Oh, you're the richest person. You're the second richest person. You're the third richest person. Or from the other direction, you're the poorest person. You're the second, third poorest person. Yes, it involves a finite amount that is that can be added or subtracted. And we're ranking. It's just saying what is above something else.
Okay. So it's going to be a finite amount of. So when you're trying to rank something, it seems like you would say that that's more of like the difference between like a corporal and a lieutenant, or a foot soldier and a general. Like that's not the difference between a 1 and a 2, right? Like this is like about power and what you can do, or what
you could think of that in terms of rank, but rank, I'm more talking about like rank on a leaderboard is more the way that the analogy of a gaming leaderboard is a good way to think of rank. Maybe that they have different amount of points though. The first person on a leaderboard has 100 million points, and the second person on the leaderboard has 90 million points, and the third person on the leaderboard has 87 million points. Like, the differences in the amount of points they have are different because the amount of points they have is like a scale. However, the ranking just cares about who has the most, who has the least, and so on.
Yeah, second place. There's a point after. Oh, you came in third place. Well, no one fucking cares. Yes. First place matters here. Yeah. Okay. Unless there's a prize for second or third place. Otherwise, it doesn't matter if the difference is between. You could have 100 million points and third place. At second place, and the next person has like 10 points. Well, you're second, they're third, neither of you won, doesn't fucking matter. Okay, so that makes a little bit more sense to me now. So for people just joining, I never had a real math teacher. I spent a long time in remedial math when I was in college. College was where I wrote my first essays and sat in my first classrooms because I'd been technically homeschooled, but also, if you really want to think about it, I never had a teacher in my homeschool environment because my mom wasn't much of a teacher and she was really busy pioneering, like literally out gardening and stuff like that. And so it's like I had books given to me, and I was told I would need to do the tests, and so basically I just cheated my way through it. Which is what a lot of people do. And by the way, regurgitating without understanding is a kind of cheating yourself. Even if it's what the system demands of you, it's a kind of cheating yourself. And so most of us have cheated ourselves with math. Other people, they get it at an intuitive level. And then some of us, we just, like, because we're doing something excruciating like this, we're able to eventually wrap our heads around it. So that's what we're trying to do, because ultimately this stuff's important. So, okay. So we're, okay. Weight is in a scale, not in a rank.
Mm-hmm. Yes. Yeah. Weight is on a scale.
And weight is a mathematical word. It's a technical term. It has a specific meaning. It's not like a metaphor. So what is its meaning?
Weight in which sense?
That's I don't know.
Weight can be used in a few senses, because weight can be a scale of its own. Like pounds is a weight, newtons is a weight. It's a type of unit for a force. You also the way that a mean or an arithmetic average works means that the difference in weight that you have matters versus the purely relative positions of these things, where median comes in.
Okay.
And these branch out into two broad families of describing things.
So you're saying that in a median, it's just purely relative and it doesn't really matter.
Yeah, well, the median is the middle number. It doesn't matter how big all of these numbers are. It just counts. It organizes them to smallest to largest, and then chooses the middle number. That is what the median is. And it doesn't care that all the numbers below it are all clustered together, and all the numbers on the other side are all like increasing, and some of them are just way up there at ridiculous levels. It just cares that half of its numbers are on one side of it and half of its numbers are on the other side of it. It doesn't care about the weight that these really big numbers do to contribute to this.
Okay. Which would actually be why the middle class has a lot more in common with the lower class than it does with the upper class.
Exactly. You're getting the sense of this. Exactly. And I call it stratification, in that there are layers and levels that just like are on orders of magnitude above each other, and things exist on different strata, on different levels. But so the fundamental difference between these two sorts of middles is that one cares about the actual values of the things, and the other only cares about the relative positions of these things within this.
Say that last part again. So
the mean fundamentally cares about the actual scaled values. It cares about how big some numbers are versus how small some other numbers. Where median only cares about their relative position in the set, ranked and ordered. When I say ranked, I mean ordered from smallest to largest. Within that, median is the middle number. Let's see, another good example. Oh yeah, exactly. Zonzi just made a very good, quick thing. If I had three numbers... Pardon?
Oh, what did he say?
It made a very good example. If I had three numbers in my data set, 1, 400, and some, it looks like
8 gabazillion.
Yeah, a 16-digit number or something like that. My median is 400. My mean, however, is going to be like a 16 or 15-digit number.
Right. Okay, here, I'm actually gonna do it. Like calculator. Let's see. I'm actually gonna go ahead and get the mean of those three numbers. So if I add those three numbers, that'll get me the mean, right? So exactly. I can add and
then divide by 3.
So what was the big number I just copied and pasted, because there's no way I'm gonna sit here and transcribe that.
Exactly.
Because it was for those. It's gabazillion, and then plus 400 plus, what was the first one? Just 1? Okay.
Yeah.
And then that equals something ridiculous that we don't have to understand. And then divide that by 3. The mean is, okay, 1, 2, 3, 4, 5 sets of 3s separated by decimals with a 2 in front of all of that. So 2, I don't...
2, yeah, it's got
so it's million, billion, trillion. So what's above trillion? So it's
quadrillion?
2. So it's 2 quadrillion. That's the mean.
Yeah, exactly.
Yeah.
So is this essence of what can happen in mean-based analysis making sense, especially when it comes to that question that I gave you?
So, yes. Yeah, the median would be 400. Okay. So if you were like, well, you're making a median income. You're making $400 per week. Okay, but someone else is yeah, exactly. I can see how that would skew. Exactly. So this is why it's wrong to talk about median household income, or at least how it skews people's assumptions about
exactly
about class. Yeah.
And the example that I remember seeing, it popped up on my Twitter feed or something, but it was just one of those like complaining about millennials and avocado toast and all that nonsense thing. but it was this person that very clearly is like, they're writing for like the New York Times or something like this. So they're very clearly not talking from their own personal experience here. They're just kind of pulling up, well, the mean income for somebody in the United States is this number. This means that you can get, like, you could, if you pay this much for your car and this much for this, and you're putting down a mortgage and all this, you should be able to afford all this stuff. Why can't all these millennials do this? This isn't that much money. And like, it's very clear that they're trying to present it as like the millennials are just undisciplined and all that. And they're also doing that by pretending that millennials have a lot more money than they actually do, because that mean include, like, that's not the mean of like millennial incomes or anything like that. That's the mean of everybody's income. And that includes all of the people that are not millennials, as well as all the people that are millennials, to generate that number. And then that number is trying to be used as representative of a group of people that it very clearly does not apply to. And you could work on the other side and you could do it by median, but the difference is about $20,000 because of how much skew there is in that distribution, how much the big numbers drag up the average. 3 blue, 1 brown is a fantastic communicator. Just some people talking in the chat about a specific YouTube person.
Right. By the way, someone shared. They were saying you should follow Numberphile. On YouTube for this stuff. And Khan Academy is also really great. Usually, the people who are really into these, usually when people recommend me a math channel that they really like, because they're usually math people, and usually so. Like Khan Academy, like whenever I try to like watch, I just can't follow.
It's like a different sort of thing. Khan Academy is practical nuts and bolts doing stuff. Like if you're like, as not a math person, the math popularizer type people would be the more appropriate sort of thing. Numberphile, they bring on like actual mathematicians to gush about what they're passionate about. They're not really there to teach you something for a classroom setting. They're there to show you interesting patterns and interesting concepts. Khan Academy is like doing the sorts of stuff you would do in school. It's the sort of stuff that if you're already doing a school-based thing, they would be doing examples that you could follow and help you accomplish the sorts of stuff you're doing.
Yeah, which when I was doing all my remedial math in college, I did have to do that. And it's like, if just, I guess the last thing I'll say about my remedial math in college was that, what does that mean? I didn't even know what remedial meant when I started going to college. I just, because of my entrance exams, they were like, well, before you're able to advance in college and do almost any other classes, you're going to have to do a few semesters of math, and it's basically high school math. And I got A's in my math, but it literally took, well, I guess I should say an average of like 3 hours per day in a week. sometimes I'd do 5 hours, sometimes I'd do 2 hours, but I had to do it every day, and I had to do it for hours, and I couldn't have distractions. And the problem with it was like I still wasn't actually learning it. I got A's in all those classes, but it's because I was learning. Oh, when I see this pattern, I apply this function, and then I'm good. And so that's all it was.
In some ways, you are correct there. It's just you were probably just every single pattern became separate, and it's like where I kind of do the same thing where it's like, oh, I'm looking for a particular sort of pattern, but like I'm giving formal names to all these things. It's like, oh, okay, I see a number that's organized like this. It's this type of number. What am I trying to do? Oh, I know what my goal is, and then my process is kind of as a result of that. It's just, to me, most of the things are the same thing. They're just applied different ways. Instead of like reacting to very specific things and knowing how to get the answer, as it were, from that. But it's just, to me, everything is more or less the same eventually. Like all of high school math is algebra to me.
Okay.
Like it just lives in a family of my brain that I think of as algebra. And then eventually there's calculus and statistics, stuff beyond that. But it not this unit, that unit, this other unit. It's a lot of common things that are similar to each other. Mean versus median.
Versus median. Is that IN? IAN?
Yes.
Okay. Okay. And then, let's see. This is a thing of rank. This is a thing of scale.
Yes.
And rank is sort of it's just relative to center. And then scale is weighted. And which means that all it really takes is a few numbers to really throw off the whole thing and all the answers. Okay, cool. What else?
Well, there's a formal distinction that you would write down for the two families of analysis this belongs to. So mean belongs to the family of parametric analysis, and median of non-parametric analysis. And if you remember when we were talking about populations, how samples have statistics and populations have parameters, this relates to that. Because like a population doesn't really have a rank.
Unless it's imposed.
Yeah. Well, like you're meaning rank in the non-mathematical sense if you're imposing the rank there. It's a little bit different.
Oh, okay.
But so these are like just big families of the sorts of analysis you can do on, and that's also the formal language. So if you like throw in like what is parametric analysis, statistic, what is non-parametric analysis, statistics, you'll find lots of stuff talking about these particular distinctions. But like roughly speaking, this means that one is like the actual scales of things, and the other just cares about the orders of things independently of the scale involved. And so there's like just going along these families, parametric analysis, and the things related to the mean. We could talk about some of these other ideas, and some of these other ideas, they mostly relate to the shape of the data. So the mean is the middle of the data. Okay. The shape, very shape. Like this is like this is the point where I would start drawing different things. But that's
you can tell me what to draw. Yeah.
Okay. So the first is just the mean. And then the second thing in the hierarchy of things related to the parametric analysis, like the mean is called the first moment, or it's the distance from zero of the middle of your thing. The next thing is called the moment. Yeah. The next is the variance. which speaks of how spread away from the mean your data is.
How spread the data is from that center.
From that center. And then the third is called
that be data are or data is?
How spread the data. Data is plural, so data are.
It's just, yeah, okay. Okay, that's
actually
right.
is works as well. I don't know.
It sounds
it's
weird,
weird.
right? Yeah.
Yeah.
Okay.
And then skew is like if skew is whether or not the top of above your mean is weighted higher than the skew below your mean. So skew says how slanted this variance goes in either direction.
I shouldn't say might be. We're talking about how slanted variance is.
Mm-hmm.
Okay.
And the fourth is called the kurtosis, which says how flat or how tailed your data is, which is really just saying, well, does all your data exist in the middle, or is all your data spread out over the entire thing? And it's called the kurtosis. But these are in increasing complexity features of a parametric analysis. This is like your normal distribution where it has like that middle peak and it's got its tails. Increasing the variance.
Hold on. I'm sorry. Okay. Bon Winter, first of all, thank you for that subscription. Okay. Ooh. Now, okay. I have to get this distinction between flat and tailed figured out really quick because I got lost. Sure. And I need that word too. I got that word. What's the word?
Oh, the word is kurtosis. Kurtosis.
Kurtosis.
Correct.
Okay, kurtosis. How flat or tailed data is, and then what's the difference between flat and tailed?
So it is if the number is very high, it means that your distribution is spreading over a very long thing. However, if it's very low, it means all your data is really clustered around the mean. It's similar to variance, but variance.
I'm getting so. No, I feel. Okay, so what does flat mean?
Okay, so you know the normal distribution, the bell curve?
Yeah.
Okay, so if I under that bell curve is 1. So if what I did is I put my hand on top of that bell curve and shoved the middle down, and the tails as they reached out, I picked them up, that would expressing a higher kurtosis.
Okay, so tailed just means that goes way out there, and that's kurtosis. Is that right?
Well, you would also raise the tails slightly, because remember you have to have all of the same area underneath the thing, and if you're flattening the top, you're by definition raising the tails.
Okay. So we make fatter tails.
Yeah, fatter tails, which means that the likelihood of getting events farther from the mean is increasing.
Okay, and so so you're saying it's like variance, because if we're talking about the how the spread of the data is from the center, when we're talking about billionaires from the median, they're going to be they're tailing, right? Whereas it's
they're
outliers.
Yeah, they are things that exist in the tail, and if you increase the kurtosis, it would be like saying that the number of people existing in the tails is increasing. Where the variance just tells you like where the tails are relative to the mean. It's like what numbers are under the tail. The kurtosis is about what percentage of the overallness is in the tails versus what percentage of the overallness is in the center.
What percentage of the overallness is in the center? Can we repeat that one last time? I'm sorry to do this to you, but I'm officially feeling really stupid.
No. Like I'm also practicing my explanation here as well. Okay. So the mean is just the location of the center, first and foremost. The variance tells you kind of the location of the tails, like how many numbers those tails spread over. The skew tells you the slant of that thing, whether I've grabbed one of the tails and yanked it upward or grabbed one of the tails and yanked it downward. And then the kurtosis tells me what percentage of the overall things are in the middle versus what percentage of the overall things are in the tail.
The kurtosis does that.
Yes, the kurtosis tells me that. And these are increasing levels of complexity, how we can talk about this shape. And the skew and kurtosis, you do not deal with these in an introductory level. But these are increasing levels of how we can talk about these things.
Yeah, okay. So I said also known as percentage in tail versus center. So kurtosis
yes,
would
percentage in tail versus center. The standard deviation.
I never learned kurtosis.
No, you wouldn't have.
That didn't come up in anything, so that's why. Okay, so but skew makes sense. Kurtosis is another way of thinking about these tails, but specifically because it's like, what if a large percentage of the number of a population is actually in the tail?
Yes.
Okay.
A high kurtosis thing is basically telling you that like your relative likelihood of being in the center versus being in the tail is like not that extremely different. Versus something with a very low kurtosis, it means you're basically guaranteed to be in the center. So high kurtosis means you're much more likely to be in the tail relative to the other something with a low kurtosis.
Servant says, what else does the kurtosis tell you? Does it give you dreams of spiders and lilies in the dawn? Dogs and Radicals, that's you, says standard deviation is square root of variance. So it's the same moment as mean for doing comparisons on the mean. Yeah, okay. So, and I feel like if we're only going to bring in one more concept that we have to talk about on day two, it has to be standard deviation.
Okay. So one more concept for parametric stuff, and that would be the standard deviation, which is see this first moment, second moment, third moment, fourth moment thing actually has to do with the units that are present here. Now. So the mean, for example, is woo, you got a rate.
Thank you, Dude Snaps, for that raid. Welcome. It's a little premature. That alert is a little premature because I'm not playing Doom at this moment. It's for those who don't have ears on it, which is really just Dan. Dan here is Dogs and Radicals for those who haven't met him before. This is my statistics tutor. This is day 2 of a crash course in the priestcraft known as statistics. It's basically statistics for plebes. I am your host, Theory Plebe. This stuff is really important for understanding how the ruling class can manipulate us using data, but also how data can be useful. And so we're just trying to get some basic terminology down for what is called parametric analysis. We're talking about variance, skew, kurtosis, and now standard deviation, which is he was about to start explaining standard deviation right as you rated in. So welcome, raters. Get comfortable. If you hate math, welcome to the club. But this part of why I've always hated math is because we're forced to just learn how to pattern recognize and then apply functions without understanding why or how they're useful or where they came from. And so one of the great things about Dogs and Radicals is that's kind of his style, is talking about that. And as a person who's a leftist, he first kind of we were already talking about philosophy of science. We were already talking about all of these kinds of things from a political standpoint on a group stream 2 weeks ago when he first offered to do this. And so the first segment of this lecture is available in the Discord. Go ahead and do the ! Discord, the command function Discord, if you want to join my Discord, and then go down to the category once you get cleared. The category is called guest lectures, and then this one is statistics and populations. So you can go find part 1 there, as well as the preamble to part 1 there. But if you don't want to watch all that stuff, you'll still hopefully get something out of this if you want to come along for the ride. So also the funny, weird thing about this chat, the chat that is on screen is not the chat that you have here on Twitch. So if you're watching it from Twitch and you want to be on the chat that's on screen or see the stuff that's been said in chat before you arrived, which is one of the sweet features of my personal website, you can actually go and join that chat there. Dude Snaps actually joined it, I think, for the first time yesterday, which was great. Love Dude Snaps. They're great. All right. Welcome. Now we're back to it. Standard deviation. Let's go.
Okay. So the complexity of this increasing family of things, mean, variance, skew, kurtosis. These are like in increasing like powers of these units. So like if your mean is in feet, your variance is in feet squared, your skew is in feet cubed, and your kurtosis is into feet to the power of 4.
Oh shit.
So none of these are in the same units of each other. These are different types of numbers. And in order to do proper comparisons to things, you need to be comparing apples to apples. You need to be comparing the same sorts of numbers to each other. So if I call mean order 1, variance order 2, I need a number that is order 1 in order to... moment is a technical definition here. It's a level of complexity. I could also say first order, second order, third order, fourth order, or first level of complexity, second level of complexity, third level of complexity, fourth level of complexity. The technical word is moment, though. So it's the first moment, the second moment, the third moment, the fourth moment. I'm getting a network error here and not seeing the screen, though.
Cool, so I can hear you.
Perfect.
So the only thing I'll say about that really quick is I think I'm following how variance, skew, and kurtosis are to the power 2, 3, and 4. Does that correlate to what you're saying about first order, second order, third order in a necessary way?
Yes, okay. Exactly. No, in an exact that same way. That is that relationship.
Okay. So variance is the first order, and it's always the first order of any data set.
Yes. Or variance is the second order. The mean is the first order.
Oh shit. Okay, that's really important to know. Okay, so before we get into variance whatsoever, we have mean. I better put that down right here.
Yeah. So the standard deviation is a first order representation of the variance.
You're gonna have to say it again in 1 second.
Mm-hmm. Yep.
Okay, so the standard deviation is, you said, what is it?
The standard deviation is a first order representation of variance. It's the square root of the variance. So it's a number that talks about the spread that has been brought down to the level of the mean to do analysis on the mean. Because you can't be like, squared numbers don't talk to unsquared numbers, not in a friendly way. So in order to use a squared number to talk to an unsquared number, I need to flatten it down by taking the square root of it.
And you're
Does that make sense?
you're saying that would be the standard deviation?
That is what the standard deviation is. It's just the square root of the variance for doing actions on the mean with this variance, because the variance is not the same type of number.
Okay. And so, okay. Talk a little bit more about this.
Okay.
I think I'm following, but I'm not 100%
so
sure.
It's a fundamental concept of mathematics here. like you need to be comparing apples to apples, or else you're not, like, you're going to end up with weird units floating around all over the place. And you create, I should draw this. I really need to be able to draw something here, because these each are like, it's interesting because variance is like an area, skew is like a volume, and kurtosis is like a fourth order thing that's kind of weird, but we don't care about dimensions in this because we just care about the relationships between these things.
Okay, so does that mean that we have to take a short break to set up a Zoom thing, or do you have a way of doing this?
I should be able to just share over this.
Okay.
Let me see how I can. So I can change what I'm looking at in my thing, and I just need to open something that I can draw on. And let's just open up Paint 3D. That should work. And new.
Hello, leftist tech support. Good to see you.
That there. And let's look at Paint 3D. Hello. Okay. So you should see now. Let's see if that popped up. Ooh, I'm going to have to flip this around. Wait, no, maybe I won't have to flip this around. Yes, I'm going to have to flip this around. Or at least
there we go. Now we see. Yeah.
And then let's make it.
Hey, while you talk, I'm actually going to switch positions so that we have a full screen on your thing so people can see it better. And then I'm going to grab coffee while you talk. So 1 sec.
Yep. Well, if I'm starting with Flatland, I'm talking about dimensionality in general. So I don't think we're going to be doing that. Let me draw.
Were you talking to someone else just now?
Oh, I'm talking to somebody else in the chat there. So here, let's see now. Let me say I have.
Okay, we can see that.
Let's draw some actual straight lines. I got better tools than. I should have opened another thing. This is not the best vector thing. Whatever. I'm just drawing. Okay, so we want something. Okay, so we're dealing with data, and we have two axes, and we have data that increase along here, and also increases along here. So what would be called the first moment of these things is like the center balance of this, which is effectively the average that all these things drag up things from the mean, from zero here. So this line that I've drawn along the center is called the first moment of this data, and because it's the middle of it all, it's the averageness that each of them fall away from the zero down here.
And that y-axis, the vertical axis, is which again? What is it again?
It's if x is just the x is the scale that each of these things are on. So this is the scale. I don't care what sort of unit this is. If I was measuring the weight of something, then it would be like grams, kilograms, pounds, something like that. Or like it doesn't matter, but it's just some sort of scale. And this is some either just like object 1, object 2, object 3, object 4, and so on, or it might be on some other scale.
So let's just say it's apples, just really quick.
Yeah,
so,
it's our number. It's our apple.
Okay, so we got one apple, we got two apple, we got three apples.
Each person. This is the number of apples various people eat in a day. So that's
okay. So one person eats one a day. Two person is. It looks like they're having 3 per day. Okay, I follow.
Yeah. So this is person number 1, person number 2, and these are the various number of apples that they get today. I need to kill. Oops. Undo. Okay. Oh, there we go. There's my eraser. I don't need that. Don't need that. Cool. And my first moment is like my average on these, and then if I take each of their distance away from the first moment, what I get is a set of numbers that corresponds to the the deviation from the mean. How far from the mean each of these things is. Right?
So that's the variance.
No, not yet. Not yet.
Oh.
Because
okay.
The
the
problem with the deviation from the mean, how far apart they are in the first level, is how far apart they are from the mean. But the problem with me like trying to get a measure of these things is that some of these numbers are negative, and some of these numbers are positive. So I need a way to be able to shove all these numbers together, in a sense that makes sense, where they're not canceling out with each other. Because if I just add all these deviations together, my sum of my deviations is equal to 0.
Oh, because it's the middle.
Yes, exactly. Yeah. The sum of my deviations is equal to 0.
Okay.
So what I'm going to do is I'm going to square each of these numbers. I'm going to turn each of these things into an area by multiplying them by themselves effectively.
What kind of witchcraft are you up to?
Yeah.
What's this going to
do? So I'm taking a second order number. So I'm finding the area of each of these things by squaring them. Because if I take a negative number and I multiply it by a negative number, I get a positive number. And if I take a positive number and I multiply it by a positive number, I get a positive number. So by squaring all these things, it doesn't care about the fact that some of them were negative.
So this is your way of converting everything into apples, essentially.
Yes, I mean, kind of, yes.
Not in the current example, but in the previous metaphor. Yeah, okay.
Yeah, and then I'm going to add all these areas together. And then I'm going to count how many things I have.
So 5 in this case.
And I'm going to divide it by that number minus 1. And the reason I subtract 1 from this has to do with the idea of degrees of freedom. And every estimate that I make basically steals a degree of freedom. But
Sorry,
let's not get into this. This is minutia here. This is like a particular. So I'm going to divide it by a number that is similar to the size.
Okay.
It's similar to n, and it's called the degree of freedom that I'm going to divide it by. It's similar to this. It's not the same thing, but it's similar to that. So effectively, I'm averaging the size of these things.
Yeah. That's basically
right?
Yeah. I got that. So you're gonna get the average of these deviations from the middle.
Yeah, and that's the variance.
And whatever the average is the variance?
Yes.
Okay.
And it's also called the sum of the squared deviations. Which is the variance.
And we're looking at the reason why. Okay. So I had already written that the standard deviation is the first order representation of the variance, which is, now you've just explained that backwards. So you've kind of reverse engineered that statement. So this is why we have to figure that out in order to get the so the standard deviation.
Yeah, degrees of freedom
where you square it all.
Degrees of freedom relates to this idea. If I want to map a data set, if you give me infinite degrees of freedom, I can map whatever you want. It's really actually very easy to do. Let me make a new. So let me demonstrate kind of the idea of degrees of freedom. It's like, this is my data set, and I want to map something to this data set, and I'm allowed all of the degrees of freedom. Cool. Let me draw my thing. Cool. I have a perfect representation of all of these things. I have no error whatsoever. The problem is, I've used all of my degrees of freedom to do that. And that thing that I've effectively created is useless.
What's the word freedom mean right now?
The amount of moving pieces is kind of a way to think about it. So in a regular data set, you start with the amount of moving pieces is equal to the size of your thing. But then I fixed something in the middle. I fixed the mean in the middle. So I basically steal I steal one of my moving pieces to fix something in the middle.
So it's a way of looking at a bunch of chaos and then saying, okay, but we're going to follow this one thing and see how the patterns of everything else relate to it.
Yes.
Okay.
And it relates to the idea of if you're not restricting your ability to model things, you can just draw a line between every single one of your data points. And like a lot of statistical analysis has to do with the trade-off between like using more variables to model your thing. In other words, using more degrees of freedom to model your thing versus how many degrees of freedom are left at the end. And each of these subsequent things basically making the mean steals 1 degree of freedom, making the variance steals another degree of freedom, making the skew steals another degree of freedom, making the kurtosis steals another degree of freedom in the way that these numbers are formulated.
Oh, okay. Yeah, because looking back at the whiteboard here, remember everybody, the mean is...
Yes, it's like a point buy system. If I want to keep creating these increasingly complex structures, I need to steal my ability for these numbers to vary relative to each other.
What's a point buy system? Is that a sports thing?
Oh, it's a D&D thing.
Oh. So in D&D, what's the example in D&D really?
Well, if I want to increase my statistic, like my attribute point for strength or dexterity or whatever, I use points, but I have a finite number of points and I have to distribute them where I choose.
Okay.
And an analysis of things in statistics is often, I want to explain as much as possible using as few degrees of freedom as possible, because my analysis depends on the ratio of how much I explained versus how many degrees of freedom I used versus how much error is left over and how many degrees of freedom I have left over.
Okay. And
kind of
the
like
reason you lose one for each of these is because they're to the order of... So it's like you're going up in order, right?
Yeah, kind of.
You lose a degree of freedom for each order?
Yeah, kind of.
Kind of? Okay.
Kind of. This is not a concept that I've had to explain at a super high level, and this is like, frankly, I know most of this concept intuitively, and I know it from the sense of, well, like, margin of error is a thing specific to a confidence interval. Like, margin of error is a specific thing that relates to a specific type of inferential statistic. Let's see now. Opening up. But yeah, this is the variance as it's calculated. Essentially, all your numbers are positive and negative, and in order to be able to add them all together, I need them all to be apples or the same sort of thing. So I square all the numbers so that they're all positive, and then I add all those positive numbers together. The skew, however, is actually allowed to be positive or negative because it's third order. A positive skew means you're skewed upward, and a negative skew means you're skewed downward. Because like a positive times a positive times a positive is a positive. A negative times a negative times a negative is a negative. Animate the error cone. Oh yeah, I could, but that's getting a little bit into once we're actually talking about inferential statistics and the sort of stuff that we're working.
And we're doing descriptive right now. We're not doing inferential.
Yeah, and so basically, if I'm not borrowing a thing each time, the numbers turn out wrong, and like that would be enough for some people. But the concept has to do with how many things I am actually estimating, how many features of this thing I'm imposing on this thing. And for each feature I impose on this thing, I need to steal an actual degree of freedom from my system to do that. Like if I want to fit this onto a straight line, for example, let me quickly bring up another
It's
one.
just this the word. I think what probably really sucks here is just the word freedom.
Yeah.
And
Freedom has to do with like variables and how a variable can separate from like, because like I can make up a number out of lots of pieces. So like I've got 3 degrees of freedom here. X plus Y plus Z is equal to 3. I've got 3 degrees of freedom here. I can vary my X, I can vary my Y, and I can vary my Z.
What does it mean to say you can vary something in this context? Are these and when you say X, Y, Z, do you mean axes or do you just mean like any number?
like axes, or a number. Like here's something I do for people. Let me clear this. Let's actually start with a very basic thing related to algebra, actually, because this kind of relates to it as well. Let me say I have a number line. I just have, so I have X, and that X is a number. So that X on its own is anywhere on that. Like if I ask you the question, where on the number line is that X? The answer is anywhere.
Because this line is X.
Yeah, that line or that, like this X is undefined. There is nothing restraining this X.
Okay.
There are no constraints on this X.
It's just a category.
And until I impose a constraint on that, I can vary over the entire span. So in algebra, so I have 1 variable and 0 equation. Therefore, I have infinite possibilities. But the moment I like take a fork and hammer it down, say with an equation, I've imposed a constraint on that. Now X can only be in one place. There it is. Because I've imposed a constraint on this one object. But
it's
let's say
like,
I don't.
It's kind of like you walk into a room and someone had primed you before you walked into the room for the color red. Now you walk into the room and whatever's red's gonna pop out, right? Like it's restricting the analysis, what you're seeing, to something specific. It's controlling for a certain, what you're seeing.
It's a constraint on the thing. Whatever X is, it must satisfy this thing that I've imposed on it. And the things that I impose on it are equal. So now let's say I don't just have X, but I also have Y. This top one is X, this bottom one is Y. And what I have is X plus Y is equal to 1. So if X was 1, Y could be 0. If X was 2, Y could be -1.
Right, okay.
So now I have 2 variables with 1 equation, and because my number of variables I have is in excess of the number of constraints I have, I'm unconstrained. Like I can be anywhere. There's still a pattern between these two things, as in when X goes up, Y goes down. When X goes down, Y goes up. But I'm still unconstrained. And until I impose another constraint, like saying Y is equal to 1, and then the moment I do that, everything else falls into place. So this is systems of equations in algebra, and how equations kind of act as constraints on your on the equations are the things that are acting as constraints, are the things that are pinning your numbers down. And basically each data point is kind of like its own variable. Like each data point can vary until I start hammering it down somewhere. That's what I'm saying when I have degrees of freedom. Like I take 100 measurements, then I have 100 degrees of freedom. Each of those measurements can be varying.
Can you use an example of how that might relate to some kind of a survey in the social sciences or something like that? And by the way, Tellensman says it's an envelope, think aviation, and Servant says, oh, fancy. And I'm not sure if Servants is speaking about what Tellensman was saying, but I'm not. If that made sense to Servants, I'm lost. I don't know what that means by the envelope and aviation. So By the way, Carpa Pax in the Twitch chat. That's really cool. The Mercy Wings on the Hi Guys emote is hilarious. It's great. I'm gonna do my thinking Jesus.
Let's see now. I can't really like this. This is just basic algebra stuff right here, and how variables act and how
Telling me flight parameter. You don't want to tear the wings off.
Yeah. Yeah. If I have more variables than constraints, I have my variables are free to just wander around, because like if I move one of them up in order to compensate for that in my given set of constraints, another one can move down.
Servants, I'm saying that if you have more variables than constraints,
yeah,
all your variables are free. That's cool. Okay. Yeah. So the constraint versus the freedom, it's that you're constraining.
Yeah, I'm constraining my numbers. By imposing a mean on this system, I'm constraining my numbers. By imposing a variance on my system, I'm constraining my numbers. And
so this is why I'm confused. I think I can articulate why I'm confused now. Anything that you're analyzing, I get that you can impose on it, but there's still okay. So in a horse race, or whether people are answering on a survey, when you're imposing these kinds of things onto that data, look, I mean, I just those things are you're not controlling the reality there. Like, so what does it mean to constrain something when it's like, well, the fastest horse in a horse race is still the fastest horse. You're not controlling that. So what does it mean? Like, the mean is the mean. What are you saying that you're constraining something?
It's because all of the things that come after the mean are dependent on the mean. Right? Because when I was doing that variance thing, the way that I created that square was all relative to the mean.
So we're doing a snapshot in time, and
yes,
okay.
And in order for me to be able to actually calculate those other things, I need to have a mean already. Because if I don't have a mean, I can't draw those squares. Because I don't have a middle number to draw a deviation up to.
But the mean is not arbitrary, is it?
Well, the mean is, like, all of these calculations, like, I can symbolically represent all that stuff without having an actual number for the mean.
Is that what you're, is that like saying that this is all part of getting to, like, if you don't know what the mean is, this is all part of finding out what it is, or what are you saying?
Well, I'd have to calculate the mean first before I could get any of those other things. It's the limiting of these relationships to each other. It's because this relationship here depends on the mean relationship already being defined.
See, I wonder if I come back and watch this later, after my brain is refreshed, if it's just going to make immediate sense to me, or if I'll be able to better articulate my confusion. But right now, I'm just kind of a muddled, confused
That's like the idea of degrees of freedom is not super. I think a few people in the chat are getting at it, but like, for what we're doing right here, it's really like not the most important thing right now.
So we're gonna, for now, just put that aside, and we'll come back to it in the future. And for now, let's just focus on what you were trying to get to, because I guess in a sort of sense, our questions about that derailed your point. You were getting at something else.
Oh yeah, no worries. You need to find the mean to make the squares, since the square depend on what that mean is exactly.
Okay. And why are we trying to make squares again? Just, can you re-summarize everything that's going on here?
Because I'm trying to articulate how spread away from that center my numbers are. Because like let me draw two separate things with different variances. So I have this one here.
We need to keep sticking with a particular example here, like
okay,
because I can just nod my head and say yes if we're talking about generalities, but I need some kind of a particular to ground myself in. I need an example of why of the way that you're. We were talking about apples. Let's keep talking about apples.
So I have two examples here where where I find the mean, and I made it really easy here. I just made three things, and I made them equally spaced, so the mean is conveniently just kind of the middle. And over here, this would have a small variance. And over here, this would have a much larger variance.
Okay, that makes sense. Yes. Okay, following.
But like, in order for me to even start making these squares, I need to find the mean first. I need to make basically an imposition. Like, I need to symbolically represent something. Now, this is the mean. And this is the symbol I'm using for the mean. I use X bar a lot of the time for the mean. X with a little hat on it.
What's the little bar? What's the little hat on the X?
It says it's average. It's the mean. It's this is just the symbol that we.
Okay, good.
The average of an X set. If my data set is X, the each individual object in that is X3, and the mean of that would be X bar.
Okay, good. Good. Yeah, I like that. Okay.
So, like, I've basically imposed an object on this thing by, because this subsequent analysis, this second level analysis, needs this thing to exist already. I'm just looking at three things. Like, where do I draw my squares? Like, where?
Right.
I need to create this middle point first.
But when you're saying you need to create the middle point, that's kind of where I was getting at. It's not arbitrary, though, is it? Like,
no, it's not. It's created in a very deliberate way. It's not arbitrary.
But okay, it has a form. Look, if you have, but isn't the mean? But how? That I'm so confused about that. Why is there?
It's created in a formulaic way.
If you have 100, the mean is going to be 50. There's not a question of that, right? Like, so why? But
like I have 100. Well, if I have two objects, and one is 0 and one is 100, the mean is 50. Yeah. But if I have two objects and they're both 100, the mean is 100.
Well, I'm getting confused here with median and mean, I think. Okay, so okay, that's a part of the problem. Okay, so because we're looking for the mean, so okay, yeah, that's right. So there's weights here, and
yes,
that's kind of what we're. Okay, my brain was totally.
Oh, okay. So
I was totally getting mixed up with median and mean there. Sorry.
There we go. Go. So we made some progress here. Yeah, no, weights are involved, and I want.
Okay.
If weights are involved, each of like the spreadness away from the middle is going to like affect where the mean is. This mean is not arbitrary. It has an equation. It's the sum of all my things divided by n.
Oh, the sum of all the things, and n is what?
The size of my thing.
The size of the thing. The sum of the things, the size of the things. Sum of the things divided by size of the things is going to give you the mean. Yes. And so some motherfucker's messing up the curve for the whole class. That's the person who's the overachiever, right? that's why. But we don't know how much or by what, and we could figure that out.
Yeah. Oh, absolutely. This is calculatable. This is a statistic. This is if I actually have numbers here, I can get this creature. But then the subsequent thing. So what comes after this is the variant, which is the sum of each of my values away from my mean squared over this, which is just what I represented. This is the deviation. This is how far away each of my things is from the mean. I square that number. so that they're all positive, and I'm not like I'm not adding them all up and they all equal 0, because half of them are positive and half of them are negative. So I add up all those squares and I divide that by one less than I had here. Because like this is all like the differences. Like these are all like differences between two numbers. Have 10 numbers arranged in a row. There are 9 separations between those 10 numbers. The variance exists in those separations.
Okay, that makes sense.
So if my initial data set is
what? Sorry, you cut out.
My 10 different things, therefore I have 9 separations between those 10 different things.
Sure.
And then if I made a number out of those 9 separations, I have 8 separations between those things.
Okay, yeah, that makes sense.
This is the essence of the pattern that we're trying to get at here.
Okay.
It's because we're making new things now.
Okay. So does that get us back to the whole...
The freedom keep collapsing as you keep leveling up this analysis, as you keep going deeper.
Servants is all... I got distracted for a second, and now there's a giant equation for variance I'm supposed to know. By the way, that's me in every math class, like the whole time. Just like...
Don't worry about it.
I was following you, and then I missed it all.
This equation, like the explanation I gave there, like here's the mean, like this value right here. This difference between the mean and the x value is that. And then I make a square on it. And then I add them all together. And then I divide it by the number of separations I have. Like that's how I make the variance. That's the equation.
Right.
And where
so
it
the
comes
number
from.
of separations that we were talking about, if you have 10 numbers, there's only 9 separations between them. That should be really easy to visualize, right? Yeah. It's really easy for me to visualize. We have 10, and then you count the spaces between those numbers.
Yeah.
That's 9. If we were to say, okay, so 9, what's the spaces between that? Well, it'd be 8. And so, but whatever the number of the things is how we use that to divide the total of the things, which is the x with the hat, which is going to be the mean, right?
Yes. Yeah.
Okay. We're almost at complete plebe brain burnout mode. So we'll just kind of like let you do a couple more things here, and then you'll give me a homework
this is
assignment
just describing
based on all
shapes.
this. Yeah.
So now let's talk about this visually and what this actually looks like.
Okay.
So if I change the mean, I'm just going to make a normally shape here.
Hello?
Hello?
Oh, it's Discord keeps clipping you.
Oh, no worries. Yeah.
I'm not sure if it has to do with I'm not sure if it's Discord's fault or if it's the connection, but...
it might be a little bit of column A, a little bit of column B. Anyway, this is what it means to have a bigger mean. So if this is one mean and this is 2 means, I can say here that mean 2 is bigger than mean 1. This is what it means to have a bigger mean. It's basically me sliding this creature that has the same shape up and down along my line. It's either up here or it's down there. It's up here, down there. It might be negative too. It could be over here. But this is what the mean is. It moves around and it says where the middle of your thing is.
Amazing.
Yeah, okay, so now we're talking about comparing 2 different means.
Now we're comparing 2 different variances.
Oh, now we're doing different variances. Okay.
Yeah. So a bigger or smaller mean just is the same shape migrated up or migrated down.
And then you square that and you get a variance or
now we're talking about variances and what a different variance looks like. So let's say we have the same mean here. So this is x, like the mean 1. Actually, I'm going to use a different symbol because technically I'm using the wrong symbol. So this is mean 1. That's a mu. That's a Greek M. Because you use Greek letters when you're talking about populations, which is, I'm just drawing a shape here, and you use letters when you're talking statistics, which are when you actually compute things. I'm not computing something here. I'm representing a shape.
What's the difference? What's that difference between computing and populations?
It's a sample versus a population. A sample is a finite number of things that I have, and a population is just a shape.
Okay.
And we use the Greek letters to represent the parameters of the population, where you use the English letters to represent the sample statistics that you're computing.
Gotcha.
And so, like, these have the same mean, but the variance here would be greater than the variance here. So variance 2 is greater than variance 1. And it's just like it's just talking about like what numbers you're expecting, because like if this is the standard deviation here, this has 68%. Here, this has 68%. And then you have 95% here and like almost 100% there. And then you have like 95% here and then almost 100% here. It's just kind of telling you how spread out your thing is, but it's the same shape. Talking about variance is fundamentally you're talking what numbers that shape spreads over. Because this, like the second one, kind of if I grab the edges of the first one and started, and the entire thing just kind of deforms slightly, but it's the same curve. It's just the curve is extending over more numbers or over less numbers. It's more compact or more. That's what a bigger
Sorry, you're getting really cutty for some reason. Restate what you were saying about. And maybe as you restate it, explain what you mean by this. You could grab it and you could, like, okay, there's a certain amount of area. And that area, if we make those tails longer or not, it's not going to, either way, you're working with the same amount of area. I get that, but I don't understand how you can just, when or how do you get to just change these things willy-nilly, like however you want? I don't, that's confusing. Well, you're talking about just being able to stretch it out. It's like, why are you able to do that?
Because a differently stretched thing is what having a different variance means. Because I'm only varying one thing now. I'm not varying both the means. So I need to fix the means first. I need to be talking about the same means. Because if I'm talking about two things with two different means and two different variances, that doesn't really nail down exactly what variance itself is doing.
Okay, so as long as we have the same mean and we're talking about two different populations or two different samples?
Yeah, two different populations for now. Okay, this is just two different things with the same middle. One is more spread than the other. So let's say let's imagine two different things that will have the same middle, but one is more spread out than the other. Let's see now. What can I think of that would work? I'm drawing a blank here.
Hey, I'm drawing a blank too. Normally people, like when we're talking about curves, they almost always talk about the 98th percentile for some reason.
Yep.
And so that's kind of over there on the corner on both sides, right? Like,
well, actually, it's interesting. So the 98th percentile here just relates to the thing that has more area, and like this is, I don't know if this is I don't know if this is 2 and then this is 3. And then this is 4. The 98th percentile here is around 4. But if this is 2, and then 3 is there, and then 4 is there, and then 5 is there, and then 6 is there, the 98th percentile here is around 6. Because the variance tells you like how my area spreads away from my mean.
Right.
Like it just covers more numbers here.
Right.
ranges over more more numbers here when I have a higher variance. Like this just has fewer sorts of numbers it can be.
And you said for a higher variance?
Yeah, higher variance means that I can spread over more numbers.
Oh, okay, yeah. Sorry, you were just on the left-hand side, on the left-hand example, when you said higher, and that I was like, no, the higher would be on the right-hand side, right?
Yeah, this is higher variance here. It's the same area underneath it. The area under these curves would both be 1.
Yeah. Just because it's the same population either way.
And this is 100% of the things. I'm talking about everything in both cases. I'm talking about the entire population in both cases. And having more variance just means that you spread over more numbers. And getting numbers further away from your mean is like whatever the standard deviation or whatever the variance is, that like what sorts of numbers you're expecting 95% of the time can either be a wider set or a narrower set. Like here, like for example, if I set, actually, let me just actually draw a normal distribution rather than.
I'm stepping away from the computer for a second, so I won't be mic'd, but I can still hear you. Okay.
Okay. I wish I had Zoom, because Zoom has a nice little thing. So let's say what I have here is a normal distribution. And my mean is in the middle, 0. Nope, doop. Versus if I make another one, make it a different color. And all I'm doing is like deforming this thing.
All right, I'm back.
So I tried to draw 2 over the top of each other. So they have the same middle.
Oh, good.
But
different
one of
colors.
them
Okay, yeah.
And one of them spreads out. So the blue for the red one, 68% of my thing are in between -1 and 1, which is to say the area of the overall thing, like 68% of that area are along the bottom between those two numbers. And these are these things that I dropped down here. And in the other one, in the blue, 68% of them vary between about -1.5 to +1.5. And the area in between -1 and 1 in the red one is the same in between -1.5 and 1.5 in the blue. Like this is just, the blue one has the higher variance than the red one. Because the thing over a wider thing, so square.
Sorry, the cutting out. Can you just restate the statement you're making?
68% are in between -1 and 1 in my red one, and 68% are between -1.5 and +1.5 in my blue one. They have the same area within those things. That's the percentage that it's talking about. The blue one has a higher variance than the red one. The blue one is more spread out than the red one. This is what variance says. This is all that having a bigger variance says. It's for a given percentage of things, a higher variance will spread over more numbers.
Which is about a cluster around the middle versus a spread away from the middle.
Yeah, this is the measure of spread. It's the spread away from the middle.
Okay.
So is variation a percentage? The area under the curve is a percentage. The variation says which numbers along the bottom axis you will range over for a given percentage. It's both of these things have 100% under them. It's just how much of that 100, like how many of those things are far away from the mean versus closer to the mean. Alrighty. So this is all that variance is trying to grab. Skew, we're not going to play around with numbers at all when it comes to skew and whatnot. I'm just going to draw what a positive skew looks like and what a negative skew looks like.
And then, as a sort of way of wrapping this up, could you kind of apply your red versus blue lines and talk about these
words absolutely.
That we've done and apply it to income distribution again, since that's kind of the example we keep kind of going back to?
It's that won't really work because that's more of a, I don't actually have the data set is the problem.
Okay.
But it more relates to skew than anything else, frankly, because skew relates to the relationship between the median and the mean. So if I have something that looks like this, this I would say skew positive or skew right. And this means the median here is like right here.
Right.
And the mean ends up ahead of the median.
Mm-hmm.
Because the weights of all these creatures drag it up.
Right.
Comparatively, something that has a left skew its median somewhere there, and its mean somewhere there.
So if we're talking poverty, that's a left skew. If
right
we're
skew.
Talking...
So here's 0, and here's positive numbers, here's negative. So here's negative numbers, here's positive.
Yeah, which is why I meant people who are... Wait. So the reason I said it would be a left skew is because there's a lot more people on the left. If we're talking, if what we're talking about is people who don't have,
it's really more about how the tail forms, because the thing is, the distribution for population. Let me draw what that would look like.
Okay.
That it isn't really either of these, because you can't really have a negative income. So so this is skew. Skew just oops. Skew just tells you, like, relative to the median and the mean, which is higher. If the mean is above the median, you're skewed to the right. If your median is above your mean, you're skewed to the left.
Okay, so now I get why that was wrong. Okay, and thank you, servants. Yeah, that makes more sense now.
Anyway, so let me quickly...
Yeah, Velu, you're right. You're right.
So the population distribution that we've been referring to would look something like this. So the median falls somewhere up here, like slightly to the right of your big peak here. Here's your median. And and this is like a power, like this is like not even a linear scale. This would be almost a logarithmic or order of magnitude scale because of how stretched this out it actually is. But your mean ends up above it. Because these have high weight.
High weight.
Yeah, high weight drags us up.
That's what quarantine is giving me in my body.
So this is kind of what the income distribution would look like, and
Okay,
it might not go like directly down to zero, but it would go down close to it in some cases. It depends like who's getting included, and you might even have like weird little, like it might not even be nice and smooth. There might be like weird little plateaus here, representing like, oh, here's all your professionals. And here's all your landlords and owners of things. And then here's all your CEOs. And here's the people that own everything.
Why are there little peaks along the way?
Well, it's just because there's clusters. There's groupings around which you will find things. It won't be like a perfectly smooth thing. There'll just be certain like, oh, like here work like these sorts of jobs, doctors and whatever, and then here's all the people that own the property, and here's all the people that own the banks.
Right. Yeah, it's just like average salaries is what Velu is saying. That makes more sense to me, because I was thinking, okay, well, if we're ordering like, because it's like, well, this one's gonna, you know, this doctor might make more than this other. Okay, but we're talking about averages, so that makes more sense.
Yeah, this is like the average of everybody, but like individual bumps might be a representation of an average within like this group of people. There's like average, they range from around here to here, and this is all the doctors. So because of all of them, there's like a weird because there are doctors around.
Okay.
But like this thing doesn't need to be like perfectly smooth. It can have like little interesting features in it that represent various other things of the thing that you're sampling. Like it might not have one mode. This is like unimodal.
Okay, so you're bringing the word mode back here after we. This is the first time we've used that word today. Can you talk a little bit about what mode is in the context of all the stuff we're talking about here?
Mode's just a cluster.
It's just a cluster.
So it's just a cluster.
And is that different from a tendency?
It's just a it's a group that you're likely that are all similar to each other in some way, and they might be, and that they stand out as a group. That's a mode. So this is a unimodal thing, because there's only one big mode. There's only one big common thing. Is this big cluster right up here, which is like around below the mean. And
it does it not help to, okay, so I gotta ask, because we use, it's kind of like the word freedom earlier. It's like, so is the word mode in statistics at all related to the way I normally use the way mode, which is like a way of doing something or a way of being? Is that at all related, or is that completely separate?
You use the dominant ways, yes. It's the dominant common ways of things. So like gender is bimodal. There are two dominant ways, two dominant peaks. It's not a binary, it's bimodal. There's two things, but there's in betweens, and there might be other spaces in between it. So
what software are you using, by the way?
This is just Paint 3D.
Cool.
So like your gender thing doesn't even really have an x-axis, but it would be like this is This is bimodal. 2 modes. Male, female. The area underneath is all 1, and this allows for variation in either direction amongst that. And then we could add, and this is just gender. And I'm not even putting like numbers in here or anything like that, because that doesn't make sense, because this is more of a category descriptive thing. But yeah, mode is how many bumps. And like there might even be other ways. There might be other like there's more in this space here. Like exactly how you categorize non-binary would have to do with like the. And then you've got like hyper male, hyper female. It's just a way of describing things. But the thing that I want to get to here is that we can increasing the way that we describe these things. Like I can describe this thing with 2 axes on the bottom and make it like duality, in which case you have 4 peaks.
Let's spend the next 5 to 10 minutes closing out the one-on-one, and then we're gonna hop into the Discord chat, and I'll play Doom Eternal for an hour, and everybody's welcome to join in. People who have questions about statistics, we'll definitely want, you'll be able to voice your questions or even just tangential thoughts right there at the beginning of that conversation. But it's also a chance for people just to hang out. And that includes everybody who's been in this chat all along, as well as people just joining. The general calls, those are a lot of fun. So, yeah, as close, I'll say my takeaway is, we spent the first week mainly talking about the difference between descriptive and inferential statistics. This has been more of an expansion on descriptive statistics and its main terms. Those main terms, I'm going to hop over onto the whiteboard and talk out loud for a second, and then you'll be able to set me straight with your closeout, because I'm sure I'm going to fuck it up. So here we go. Mic working, we good?
I hear it.
You hear it, all right. So we talked about mean, variance, skew, and kurtosis, each of which is a different order to a different power. Standard deviation has to do with distance from the mean. Is that right? But it's the first order variation. Representation of the variance.
Yes. For an apples to apples comparison.
Yes. And this is all within the sort of, this all has to do with parametric analysis. We're not doing nothing we've been doing has been non-parametric, right?
No. Aside from understanding skew in terms of it's like where the mean is kind of relative to the median. That is something that the skew does tell you, and that's the same either way. Parametric.
That's the same either way. Okay. So skew is about the distance from mean to median. Is that right? Yeah, and kind of like, if there wasn't any skew, they'd be more or less on top of each other. But when we start skewing, we effectively are moving one of them more than the other. Okay. And then kurtosis.
We didn't really get it.
We'll just.
But that's modifying the shape itself. Like the first couple, the mean and the standard deviation, don't modify the shape. The skew, left and right, and then the kurtosis flattens it while either lifting up one end while flattening the middle, or flattening the ends while lifting up the middle.
Okay, cool. And oh yeah, mean has to do with scale, whereas median has to do with rank. Scale is weighted, rank's not. So, and that weight makes a lot of sense, because if you have the overachiever in class, or if you have the billionaire class, either way, there's like that significance and that pull, that sort of gravity that they have on the rest of the distribution. So, I don't know if I'm talking about that right. Does that make sense?
No, the gravity of the distribution, that is a way of thinking about it that intuitively makes sense. Yeah.
Okay. And then I guess the last thing, before I turn it over to you to make your closing remarks, before we go ahead and we open up the Discord call and the general chat, and then we hop into game mode and after time. I'm just curious, like, what would be the homework assignment so that I can maybe, what I would like, I think, and for anyone else following along and kind of doing this course on their own, this stuff is going to be linked in the Discord. Kind of what I would ask from you, I guess, is some kind of an assignment that has a set of different problems that requires me to basically master what you've already said today. Mm-hmm. Mainly, not just these terms, but also how you, like, I don't know, how would we apply this? Yeah.
Well,
in homework.
I would probably make various sets, and I would ask in this set which set has the higher mean, or like I'd give 2 sets and then ask the question which of these sets has the higher mean. I'd give 2 almost identical sets and then ask the question which set has the higher variance, or like that type of thing. It would be direct comparisons, and you'd have to identify like what feature of this makes it more of one of these things or less of one of these things, if that kind of thing would make sense.
Okay, cool. And then do you kind of have like a natural direction that this is going to go in? So, because it made sense that we went from, you described the difference between descriptive and inferential, and then we moved into descriptive, and then you've laid out its main terms. Is there kind of where's this going? Where's the next step?
Well,
do you know?
I have a couple options here. I could move into the mean analysis of, this is the standard deviation, this is how I play around with the standard deviation, and this is how I compare it to a standard deviation type thing. Or I could go down the median branch and fill out the stuff related to the median, because the median, to talk about the range involving the median, and the difference between those becomes the range.
We lost about 8 words. What you just said.
Okay. So move down the mean path of talking about the normal distribution and analyzing things in terms of the normal distribution, or backtrack and go down the median path and talk about the spread and the different things that go on in non-parametric analysis.
So one is more parametric, and we just go deeper. The other is go into parametric.
Or non-parametric, but yes.
Or not, non-parametric. Yeah, okay. Cool.
Which is really just describing things like percentile and stuff like that is kind of a non-parametric thing.
Oh, to talk about the percentile?
Yeah, like
I need to know about that.
So. Yeah, the first and third quartiles is if the median is the 50% mark, the halfway point. The first quartile is a 25% mark. The third quartile is the 75% mark. And then the various percentiles is that percent mark.
I guess if you're going to go in that non-parametric direction, what would be useful is since the homework's going to be dealing with this stuff, that it will in some way continue to build off that still. So, and obviously going with the mean path builds off this, but also you could kind of do it through contrast, right? So you could still be, you can kind of, or at least we just do a kind of a recapitulation of the previous week, either way. Oh,
actually, I could do non-parametric things and then ask, like, just comparison wise, because it's very visual. You can really start telling this variance and skew thing, less the kurtosis one. Or actually, if you got the right mindset, you can do the kurtosis one too. But you can kind of visually see those different things once you rank out your numbers and kind of look, just kind of, it's called a box plot. But this uses the various non-parametric things, and based on how wide it is, how wide the middle thing is, like, is the middle slanted is living on this end, or is it living on that end compared to my edges? Like, all that variance, skew, kurtosis will appear visually when you're doing non-parametric stuff.
Cool.
So I'm gonna write a couple notes related to this down,
Yeah.
and I'm gonna create something here.